Hello, you are getting my voice?
Yes, sir. Good afternoon, sir.
Okay. Good afternoon. Just wait 2 minutes, then we will start the session. Okay. So now I think the whiteboard is visible for all of you. Whiteboard is visible. Okay. So today we will discuss that is the parallel binary adder as well as the BCD adder. Okay. So I think in the last class we have discussed about the half adder, full adder, half substructure, and full substructure. Now we will discuss that is the parallel binary adder. Okay. So this is parallel binary adder. So you already know what is adder. So adder are the combinational circuit which are used to add two binary numbers. And one thing, for example, if one needs to add two single bit binary digit, then we can use the half adder. So for the case of half adder, we already see that there is two input and two output. Okay, and if in that case, while if there is an additional carry as an input which needs to be added along with them, then it is called the full adder. So for the case of full adder, we can see there is three input and two output. Okay, now if we want to add a binary number which has the multiple bits in it, in that case it is not possible with the help of half adder and full adder. Okay, in such case we need arrays to use the parallel adder. Okay, that's why we will now study what is the parallel adder. Now before going to start the parallel adder, mainly there are three types of adder. Here it is, one is serial adder, another is parallel adder, and third one is look ahead carry adder. But in your syllabus, only the parallel adder is there. Okay, now for the case of parallel adder, mainly for 4-bit adder, we need one option, that is 3 full adder and 1 half adder required. The second is, or 4 full adder is required to construct the parallel binary adder. Okay, so here the parallel adder is used to add group of bit, and to add to n bit number, it requires n minus 1 full adder and 1 half adder. Okay, so here I have said this is for 4-bit adder. Or another option is that in full adder or 2 minus n up adder and n minus 1 OR gates. This is the option, right? From this you can easily construct the parallel binary adder. Okay, now this parallel binary adder is also called the ripple carry adder. Okay, so what is ripple carry adder? Parallel binary adder is called the ripple carry adder. Now suppose I am here drawing the 4-bit binary parallel adder. Like this. This is a block. This is the out. This is A3. This is B3. So this is C4, C3, and this is suppose S3. This is C3, C2. So this is A2 and B2. This is S2. Now this is C2, C1, and this is C1, C0. So this is A1, B1, and this is A0, B0, and this is C in. This 0, and this is S1, and this is 0. Okay. So this is here, this is a 4-bit parallel binary adder circuit, and here you can see the input to each full adder will be here. This is AI, BI, and CI, and the output is SI and CI plus 1. Here I varies from 0 to 3. And one thing here, the carry output of the lower order state, this is the lower order state, is connected to the carry input of the next higher order state. Okay, and this type of adder is called the parallel binary adder or triple carry adder. Now here in the least significant state means where A0, B0 and C0, okay, which is 0 here are added, resulting in the sum of S0 and the carry one, that is C1 here. Now this C1, this carry becomes the carry input into the second stage. Here you can see this is connected from the first to connect his with this second. And similarly, in the second state, here the A1, B1 and C1, these three are added with resulting in S1 and C2, and this C2 here, this C2 is are added resulting with S2. Okay, in the third state here, in the third state, that is A2, B2 and C2 are added resulting in S2 and S3. And in the fourth state, here you can see here it is A3, B3 and C3 are added resulting in S3 and C4, which is the output carry. This is the output carry, and the circuit result in a sum, that is S0, S1, S2 and S3, and the carry output, that is C out. Okay, so this is the main concept of 4-bit binary parallel adder. Okay, so is there any doubt how it is working?
सर एक बार रिपीट कीजिएगा ना फिर से इसको.
ओके, यहाँ पर देखो, ये 4-bit बाइनरी पैरेलल एडर है, ठीक है. सो यहाँ पर चारों हम फुल एडर लिए हैं, चारों फुल एडर में है 3 करके इनपुट. तो लीस्ट significant state, that is the right one, that is here it is A0, B0 and C0 are added resulting in the sum, that is S0, and here the carry is C1. Okay, now this carry C1 becomes the carry input to the second state. Carry input to the second state. Here you can see this is the C1 also. Just 1 minute. And this process is going on up to this. Here you can see in the second block, here the input is A1, B1 and C1, and here the carry is C2, and this C2 becomes the carry input to the third state. Here the input is A2, B2 and C2, and here the carry is C3, and this C3 becomes the input of the fourth state, like that. Okay, and the circuit results in a sum that is here S0. From this it is S0, from second block it is S1, third block S2, and the fourth block S3, and the carry output, that is overall carry output, that is C out here. Okay.
Okay, sir.
Okay, so now actually in the market IC is available for parallel binary adder. Okay, what is the number of IC? That is IC 7483. This is for the 4-bit parallel binary adder. I am just erasing these things. Suppose this is 7483. Suppose this is C in and this is C out. So here, suppose this is Y3, Y2, Y1, Y0, and this is X3, X2, X1, and X0. And this is suppose F3, F2, S1, and S0. This is a logic symbol of IC 7483. This is for 4-bit binary adder. Okay, it is available in the market. Here it contains the 4 interconnected full adders, and here you can see that it has 2 4-bit input. One is X0, X1, X2, X3, and another is Y0, Y1, Y2, and Y3, and a carry input, that is C in, and in the LSB state least significant, and the output at the 4-bit sum, that is S3, S2, S1, and S0, and the carry output, that is C out from the most significant bit. Now 2 or more parallel adder block can be connected in cascade to form the addition operation or larger binary numbers. Okay, so how it is connected here? Suppose this is one IC of 7483. Okay, so next is just 1 minute. Okay, so this is 7411. Cascading means, you just watch here. So suppose this is another, so this is 7483. This is C in, and here this is C out, and C out. 2, 3, 4, 1, 2, 3, 4. This is X7, X6, X5, X4, and this is suppose Y7, Y6, Y5, Y4, and here the full sum for here, this is 6 is 5 is 4. Okay, so here you can see the cascading connection of 2 7483. This is the one IC 7483, and this is the another IC of 7483. Okay, the four least significant bits of the number are added in the first adder, and then the carry output of this adder is given as the carry input to the second adder, which adds for most significant bits of the number, and the output carry of the second adder is the final carry output. Okay, so this is the cascading of 27483. I see. Okay, is there any doubt? Okay, so there is no question, so I assume that you have no doubt. So our next topic, that is the BCD adder. Okay, you already you already know the concept about the BCD, binary coded decimal. Okay, and just few minutes ago we have discussed about the parallel binary adder. Now the topic is BCD adder. Before going to start the BCD adder, I am requesting you all the participants write your name in the chat box for the attendance. At this moment, there is 18 students in the class, but here I am watching only 15. We are getting the 15 response. सबने अटेंडेंस दे दिया? Okay, so this is a this figure is for the block diagram of BCD adder. I'm first drawing the block diagram, then I will explain. X3, X2, X1, X0, and this is Y3, Y2, Y1, and Y0. C in, C out. Sum 2, sum 1, and sum 0. This is a decimal adder. Okay, so here this is a block diagram of a BCD adder, and a BCD adder is a circuit that adds two BCD digits in parallel. Here you can see one BCD digit, that is x0, x1, x2, and x3, and another BCD digit, that is y0, y1, y2, and y3 parallel, and produce a sum digit which is also in the form of BCD. So here the sum digit means sum 0, sum 1, sum 2, and sum 3. And one thing that you already know in the concept of about BCD, a BCD adder must include the correction logic in its internal construction. Okay, so here there is two 4-bit BCD input. This is the one input, and this is the another input, and one carry input. This is C in, and there is 4-bit sum output, that is, this is the sum digit, you can say, and a carry output, this is C out. Now here the sum output is also in the form of BCD. Here you can see. Now the BCD adder circuit must be able to do the some points. What are the points? First, add to 4-bit BCD numbers using rate binary addition. Number 2, if the 4-bit sum is equal to or less than 9, the sum is in proper BCD form, and no need for correction. Number 3 is that if the 4-bit sum is greater than 9, or if a carry is generated from the sum, the sum is not in the BCD form. Digit 6 should be added to the sum to produce the BCD. Result. This point should be followed for the BCD adder. Okay. So I think whenever we already discussed the concept about BCD, in that sense you already know these rules. Again, I am here repeating these things. I think it is already, you know these things. Yes or no?
Yes, sir.
Okay. So now suppose this is the form digit, this is the uncorrected BCD sum, and this is the corrected BCD sum. Okay. Now here, suppose this is C3, S3, S2, S1, and S0, and this is C out, S3, S2, S1, and S0. Okay. So here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So if I write here in the form of BCD 0, so this is 0, 0, 0, 0. So I am just here, I am not writing here. Okay, so up to 9, you can see that there is no up to 9, you can see the sum is in the proper form of BCD, in the form of BCD, no correction is required. But when it is from the 10 to rest of the part, in that sense there is the, actually from the 10 there is a correction required from the print. And just few minutes ago we saw, to correct the digit form we should add the 6 or 0, 1, 1, 0. Okay. So almost the time is over, so your home task is that from 10 to 15, first in your copy you should write normal in binary form. Okay, 4-bit. And here after that simultaneously you should write the corrected BCD form, because you already know how you can convert uncorrected to corrected form in the sense of BCD. Okay. So in the next class I will see these things, and I can choose randomly anyone to show your copy, and I will see that how actually you does in your paper. Okay, I think you are getting the point.
Yes, sir.
Okay, so this is for today's class. In the next class, we will discuss the another topic. Okay, thank you, class, for your participation. Thank you all.
Thank you, sir.
Thank you, sir.